Okay, good morning, everyone, and welcome to those online as well. So today it's my pleasure to introduce Detlef Knappe from North Carolina State University. Detlef did all his degrees at the University of Illinois and then immediately went to North Carolina State and has been there ever since. He's part of their Science Technology Center for phosphorus sustainability and also the Center for Environmental Health Effects of PFAS. And as North Carolina is one, like Minnesota, is one of the hot spots for PFAS contamination exposure. He's been at the center of that. He's going to talk about that today. Two quick announcements. If you're a professional engineer and need your ethics credit, there's little PDH certificates up front and online. I think there's some instructions put in the chat for that. And then for the graduate students, there's a chance to chat with Detlef this afternoon at 2:45 up in the main office. So with that, I'll turn it over to you.
Great. All right, so microphone is green, so hopefully you can all hear me well. Well, thanks for the invitation and thanks for the introduction, Bill. So I'm here to tell you a little bit about the North Carolina PFAS story and specifically our work with impacted communities also. And of course, a lot of this work is done by my talented grad students and postdocs. This is a photo that was taken in May of 2021 after we had all gotten our first COVID vaccines and had a party in our backyard. The photo on the left here is a photo of us sampling on the Cape Fear River, which is central to this story. So just a very brief introduction in terms of what are PFAS. PFAS stands for per and polyfluoroalkyl substances. They're synthetic chemicals. They're really not naturally occurring at all. And they enter the environment either as a result of the manufacturing processes, and that's a big part of the story here, but also in the end, the production, use, and disposal of consumer products, right? So in the end, all of us are part of this story because wittingly or not, we are purchasing a lot of products that contain PFAS, and therefore we all contribute to the contamination. So some of the key consumer products that you probably are aware of, nonstick cookware, food contact materials. So there are a lot of efforts now to phase out PFAS in food contact materials, but things like hamburger wrappers, popcorn bags, cupcake paper holders, all of those have a chance of being treated with PFAS. There was a study that was done a few years ago that showed that about half of the paper plates are treated with PFAS. The other half is not. When you go to the store and buy it, you don't know, right? We just don't know what how we're contributing. Water repellent fabrics, Gore-Tex jackets, tents, a lot of outdoor gear, which is also sad, right? We think we're enjoying nature and feel in touch with nature, but we're buying stuff that is often treated with PFAS to make it water repellent. A lot of coatings, carpets, sofas, couches have treatments for stain repellency that contain PFAS. And then a really big source of PFAS in the environment is also AFFF, aqueous film forming foam, which is used for extinguishing fuel fires. And there is also efforts underway now to create fluorine-free foams to prevent the introduction of PFAS through that route into the environment. I have a couple of links here that are perhaps of interest. One is the 6 classes link from the Green Science Policy Institute that introduces you to harmful chemical classes. One of the 6 is PFAS. So if you want to learn more about that, go there. PFAS Central is also a very nice website where they kind of collate a lot of information about PFAS. And among things that you can find there is a link to PFAS-free products, right? So the last time I bought some hiking boots, I went to that website and bought a PFAS-free pair of boots. So the topic of PFAS, once you start working on it, can be a little bit daunting at first. There's thousands of different structures, of which very few have been studied in detail. This is a nice paper by Wang et al. From 2017 that talked about the never-ending story of PFAS, and they show this family tree, and you see at the time in 2017, papers since 2002, the perfluorocarboxylic acids and sulfonic acids, right? There were lots of papers on those. But then when you start going into some of the other classes and subclasses, the number of papers on those compounds are very few. And in this talk, I'm going to talk primarily about PFECAs and PFASas. You can see at that time there were very few papers on those compounds. EPA, as of August of 2022, has a database of over 14,000, almost 15,000 individual PFAS structures. It's very difficult to understand the significance of many of those, the vast majority of those structures in terms of occurrence and health impacts, because we lack analytical standards or just reference materials for those compounds. So we can't even do some of the toxicological work, for example, to assess how toxic these substances are. So why do we care about PFAS? For one, many PFAS are persistent in the environment, or if they are degradable, they turn into persistent products. So for that reason, they're also known as forever chemicals. I sometimes don't like that term so much, because the forever chemical part really relates to environmental persistence in a sort of global sense, right? But they're not necessarily forever in the river or forever in people, because we can shed them. But in nature, they don't break down. Some of them are bioaccumulative. So the half-lives of PFAS are quite long in people. So you can see here from months to years, and that's pretty impressive, right? If I ingest 10 nanograms of PFOS today, 5 years from now, I still have half of that in my body, right? So it's very easy to see how these compounds accumulate in people. And compared to levels of PFOS in water, the levels of PFOS in human blood serum are about 1,000-fold higher, right? So they really accumulate. And they're toxic, right? So they're known to harm the immune system. They are toxic to the liver, and PFAS and PFOA have been also labeled as carcinogen by the IARC and EPA. And PFAS are also quite mobile, and as a result of that, they move around the globe, and they're in places that are very far from where the production and use occurs. And so we see PFAS also in the Arctic, the Antarctic, right? And PFAS in polar bears and so on, right? So there are impacts in communities that are very far from the sources of the releases. So little lesson from North Carolina here. So this is the state of North Carolina. Virginia would be here, South Carolina here. And within the state, we have the Cape Fear River watershed. It's the largest watershed in the state. It serves about 1.5 million people as a source of drinking water. And then in the central part of the watershed is a fluorochemical plant. This was initially, it was called Fayetteville Works, was initially built by DuPont and is now owned by Chemours. And through air emissions and subsequent deposition, private well communities right around this facility are heavily impacted. And so I'll talk about that. But the facility also released wastewater into the Cape Fear River. And as a result, the PFAS traveled down the river, and there's an important drinking water intake about 90 miles downstream that serves a 3-county area down near the mouth of the river. So a little timeline here then. So this is what the facility looks like from an aerial view in Google Maps. The Cape Fear River is right here. The soil and groundwater under this facility is extremely heavily contaminated, right? Milligram per liter levels of PFAS. Groundwater moves and seeps from the site into the river, right? So that was one important source of PFAS. Initially, the plant had in essence, a wastewater ditch through which the water was, all the wastewater was released to the Cape Fear River. After a while, they built a wastewater treatment plant to remove things like BOD, but that plant didn't remove any PFAS, right? So the PFAS still reached the river. And so this plant was built in 1980, and the purpose of this plant is to make what's called vinyl ethers. So these are fluorinated vinyl ethers that are building blocks for fluoropolymers, right? So when you look at how you get to Teflon, there are many steps involved that happen at different points in the country. They make HF in Texas, and then they make tetrafluoroethylene in Arkansas, and then they make vinyl ethers in North Carolina. And then that goes to Parkersburg, West Virginia, or Dordrecht in the Netherlands, where they actually make Teflon, right? So there are many steps involved in many different communities that are impacted. So the purpose of this plant is primarily to make building blocks for fluoropolymers. And I would say this plant operated more or less unchecked until about 2002. And in 2002, the plant started making PFOA, the compound shown here. And the reason why DuPont started making PFOA was because the 3M company, which is located kind of close to here, started to phase out production of PFOA, right? 3M was a little bit ahead of its time in terms of stopping the production of 8-carbon fluorochemistry, and so DuPont needed PFOA as a processing aid to make Teflon, and so they started making it in North Carolina. And by 2002, there was enough known about PFOA that people in our Department of Environmental Quality felt we need to pay attention to this. This could be a problem, right? And for example, very soon after that, there was a small water treatment plant that was built downstream of the facility, and our DEQ required that this plant install granular activated carbon treatment in case PFOA would spill from the plant. Anybody watch the movie? Good. If you haven't, please do. It's really a great movie. And Rob Bilott, the lawyer who's the protagonist in the movie, I've met him several times. He's really a very important piece of the PFAS story in terms of bringing it to the forefront of our awareness of the impacts that fluoropolymer manufacturing has on people. So with the production of PFOA, some EPA researchers were very interested in seeing whether the plant was actually releasing PFOA into the environment. And they collected a bunch of water samples in the Cape Fear River watershed. And the first paper on PFAS in the Cape Fear River came out in 2007 in ES&T. And so I want to highlight here Andy Lindstrom and Mark Streiner. They've been instrumental in my PFAS journey. They're EPA scientists in Research Triangle Park. And I actually called up Andy Lindstrom back in 2010 because I wanted to start a little study on activated carbon absorption of PFAS, but I didn't have a mass spec in my lab that could measure PFAS. So I called them up and said, hey, would you be willing to work on this together? And they said, sure, yeah, we'd be happy to. And so from them, I learned pretty much everything on how to analyze for PFAS and a lot about just background information of PFAS in general. So here again, North Carolina, Cape Fear River watershed. They took lots of water samples up and down the entire river, and the top 11 sites they highlighted in this watershed. Number 5 is the location of the fluorochemical plant. It's the wastewater ditch from the fluorochemical plant. So what you can see is that most of the most impacted sites were upstream of that facility, right? So there are other sources of PFAS out there that are really important, very much in the headwater region of this watershed. And we're still working on identifying some of those sources. What's interesting is that C8, PFOA, was the dominant PFAS at the time in most of the water samples, except for the wastewater ditch from the fluorochemical plant, where PFHPA was dominant, and then in the Little River, where PFOS was dominant. And the Little River drains a large military installation, and so this is more of a AFFF impact. So the wastewater ditch and the Little River. So that was that paper came out in 2007. In 2009, something important happened. A couple of things. One, DuPont also wanted to, or was maybe kind of pushed to, phase out PFOA production, right? And there was just building evidence that PFOA is just not good for people or the environment. So DuPont wanted to replace PFOA with Gen X. So the structure for Gen X is here. It has an ether-oxygen linkage, so that makes it a little bit different. But in the end, it still looks like a PFAS, right? But now it's a new chemical about which we know almost nothing, right? So we have to start over. And in their marketing materials, DuPont at the time says that Gen X has a favorable toxicological profile, right? We'll get to how great or bad Gen X is a little bit later. The other thing that happened in 2009, well, so let me say, in the EPA and DuPont worked on the conditions under which DuPont was allowed to make Gen X, right? So it's called a consent order under TSCA. And it basically, one of the stipulations in the consent order was that DuPont and any of its customers need to capture 99% of the Gen X that is being produced or used. So there was basically a requirement to capture most of it and prevent it from entering the environment. The other thing that happened in 2009 was EPA for the first time issued guidelines for what are safe levels of PFOA and PFOS. They were provisional health advisory levels, which really covered only relatively short-term exposure. And the levels were 400 nanograms per liter for PFOA and 200 nanograms per liter PFOS. And so that gave us a first sort of sense of, okay, well, these are pretty low levels were pretty low levels at the time, right? We regulate most drinking water contaminants that are organic pollutants at the microgram per liter level, right? So here we're talking about fractions of micrograms per liter. A little bit on greenwashing here, right? So if you go to the store and buy a Teflon pan today, you probably see tags like this, right? No PFOA, PFOA free. And when you see that, maybe you feel pretty okay buying this pan, right? But really what this sticker says is this pan was made with Gen X, right? So in 2012, we were already working now with EPA, and we had our first PFAS project. And besides staying in the lab, we started to go out into the field more. And we really, based on this 2007 paper, we became just more interested in identifying sources of contamination. And around this time, DuPont had issued this pamphlet where they identified the structure of Gen X, right? In the consent order, it was actually kept as a proprietary compound. So there was no information about its structure. And so it was just this compound that was kind of cloaked and in this document, right? So if you read the document, it said under which conditions DuPont was allowed to make this compound, but it was not known to the public what that compound was. But for whatever reason, DuPont made this pamphlet in which they actually put the formula for Gen X. And it so happened that Wellington Labs, which is a manufacturer of analytical standards in Canada, was selling Gen X as a authentic standard. And their reasoning at the time was that hexafluoropropylene oxide, if it's released into the environment, it may actually lead to the formation of hexafluoropropylene oxide dimer acid, which is Gen X. And so we were able to buy the standard, incorporate it into our mass spec method, and start running with it, right? So we had hundreds of samples that we actually analyzed from the watershed from another project where we were interested in bromide, a disinfection byproduct precursor. And so we all of a sudden had a wealth of data on PFAS in the river, including Gen X. And we did find it in all of the samples downstream of the fluorochemical manufacturer. In 2014, we worked together with utility in Wilmington, North Carolina, and we traced PFAS through their treatment plant and learned that Gen X was also in the Finnish drinking water. And in 2015, around this time, Mark Streiner was told to stop working on PFAS at EPA. So it's an important lesson here, right? So if somebody tells you what to do or not to do, you can be creative, right? So he said, okay, I'll work on non-target analysis. And his superiors were excited about that. So, well, it just so happened that he found a lot of PFAS using non-target analysis, right? So he really kept working on PFAS, even though he was told not to, and found a lot of interesting structures apart from Gen X, right? So Gen X is here. And like many PFAS, they occur in homologous series. It's one way of teasing out PFAS structures in the wealth of non-target data. So here you have a sequence of PFAS that differ by one CF2 group, so by roughly 50 AMUs. So this was one homologous series, and there was a multi-ether series. These differ all by a CF2O group. And then there was also something called Naphthalene byproduct 2, that is a product that is emitted when they make naphthalene polymer for these hydrogen fuel cell membranes, right? So clean energy is not always that clean. what all of these compounds have in common is they have one or more ether linkages, right? So that's one of the new pieces of the chemistry. And as a result of this, as a result of the phase out of PFOA and PFOS, industry has developed lots of new chemistries, right? Maybe they replace one fluorine with a hydrogen or one fluorine with a chlorine. And all of a sudden you have something new about which we have no information, and we have to kind of start over in terms of assessing the importance of this compound from a toxicological perspective. So in 2016, an important thing that happened was that EPA issued health advisory levels for chronic exposure to PFOA and PFOS, and they dropped the level to 70 nanograms per liter as the sum. And that really got us into high gear. And we published a paper in ES&T Letters. My postdoc Mei Sun, my master's student Elisa Arevalo, and Mark and Andy. And we basically reported on not just Gen X, but also the other fluor ethers in the drinking water of Wilmington and other communities in the river basin. So Wilmington, North Carolina, back in the days between 2013 and 2015, all the utilities serving more than 10,000 people in the US had to participate in the unregulated contaminant monitoring rule. It was the first time we learned about PFAS occurrence nationwide. Detection limits at the time were pretty high. And in Wilmington, the UCMR3 data only identified perfluoroheptanoic acid among the 6 PFAS in their drinking water, right? So, and the maximum concentration they measured was 27 nanograms per liter. So they really thought they had not a problem at all with PFAS as a result of the UCMR3 data. But our data suggested that the PFAS levels were higher. The traditional PFAS levels were somewhere on the order of 150 nanograms per liter in the water, and the sum of all the things that we could measure was close to 600. And so here's maybe a first sort of challenge that relates to since this is an ethics lecture, what do you do when you have data like this, right? So we had this data, some of this occurrence data since 2012, the data in drinking water since 2014. This is what we knew. But in addition, we knew there was also a lot of other fluor ethers present, but we couldn't quantify them, right? Because we did not have authentic standards for those compounds. So between 2014 and 2016, our research group was primarily interested in quantifying the rest of the ethers. At the same time, I had started showing these data sets to our DEQ, to the drinking water plant. I presented it at conferences. And I would say it didn't really stick very much, just like PFAS are non-stick, right? And part of it was that, prior to May of 2016, the provisional health advisory levels, if you sum them up, they were summing up to 600, right? And so here we're looking at about 600 with the dominant contribution from a compound with a favorable toxicological profile, right? So people didn't really get all that excited about it. And I thought people would get more excited about things if you look at the Gen X in red here, the mass spec response for Gen X relative to some of the other ethers, you can barely see it, right? So we knew there was a ton of other PFAS in the water, but I couldn't tell you what the concentration was because we lacked standards to calibrate the instrument, right? So we tried to do this semi-quantitative analysis. We try to buy standards that looked similar and try to develop response factors, right? But in the middle of all of this, EPA dropped the health advisory level down to 70, right? And now 600 actually look pretty high. So I told my postdoc, we need to get this out, right? We need to publish this, and we'll see whether the journal will accept that we can quantitate everything in our samples. And the paper did get published, and so this is one of the figures in the paper that basically shows, yes, there's a lot of other compounds in here at much higher levels probably than Gen X. And this is an important problem. So even with this published paper, I went back to our DQ. I distributed to the Division of Water Resources folks in our department, EPA Region 4, the drinking water plant, and people still didn't quite know what to do with this, right? And maybe for many of the right reasons, right? If I tell you there is probably a high concentration of PFMOAA in the water, but I can't tell you whether it's toxic or not, people are like, you know, like maybe not very alarmed. To me, this seemed pretty bad, but in our framework of how we regulate things, we only regulate things once we know it's toxic, right? Only once a chemical is proven guilty, if you will. So, you know, it took a couple more years, and I should say that, you know, so now we're at a time where the plant was owned by Chemours, no longer by DuPont, right? So DuPont spun off their fluorochemical business to form a new company called Chemours to probably just put all the liabilities into this new company, right? And get rid of, the DuPont got rid of its liability, right? DuPont will now state that they never made PFOA, right? It's pretty amazing. There's a very nice New York Times article on that. I make it a habit to really not take anything from industry. No money. I try to really keep industry at arm's length. I did make one exception. Chemours offered us and EPA standards for the compounds that were not commercially available. So I talked with Mark and Andy about this, and we decided, well, we'll accept these standards to at least try and quantitate these compounds. So, you know, if you look at this archived sample from the Wilmington drinking water source in the Cape Fear River, you know, the traditionally measured carboxylic acid summed up to 120 nanograms per liter. And the sulfonic acids to 45 nanograms per liter. You know, this is, you know, somewhat high, but nothing out of the ordinary. But the fluoroethers summed up to 130,000 nanograms per liter, right? So they were drinking 130 micrograms per liter PFAS in this community, probably for decades. So the really important piece for getting attention in the end was a newspaper article. I'm pretty reluctant to actually talk to the press. I sometimes do, but most of the time, I barely answer my office phone anymore because half of the time it's a reporter. And often it's like, I have a deadline in 30 minutes. Can you give me a quote, right? And I'm like, no, I don't do that, right? Because you can twist a quote so many different ways, and you can't put the story in a 160 character tweet, right? So, but this reporter was kind of a little persistent. I'm sometimes a little persistent too, right? I keep talking out to our DEQ people, and I just make it a habit, right? Like every quarter or so, I tell them about what's new. So when we talked, the first question I asked him, "What's your deadline?" And he said, "I don't have a deadline." I was like, "Oh, cool." And then he showed me a bunch of the things he had already worked on. He had gotten like documents from Chemours in the Netherlands, from the Dutch EPA, and he had dug very deep into this story. And so for the next 2 months, he worked on this, and we had a lot of phone conversations. And he wrote this article with a headline that has a bit of a flaw. Apparently, his editor wanted that word. What's wrong with this headline? What's a toxin? A toxin is a natural poison, right? Like ricin would be a toxin. A synthetic chemical is really called a toxicant. But toxicant doesn't sound so great, right? So, but be it as it may, the point was really the content of the article, right? And when this article hit the news 6 months after our ES&T letters paper came out, the community was really upset. And it wasn't just people, it was the mayor, it was the county commissioners, it was Republicans, it was Democrats, it was independents, right? It was really something that people didn't like. And the thing that they really didn't like was two things. One, this chemical nobody ever told the water plant or the community that this was being discharged into the river, right? So this lack of informing people got people really upset. And the other was that we didn't really know how toxic this stuff was, right? In the end, the fear of the unknown was greater than if we would have said, well, the risk of this is X in a million, right? It was, we don't know how bad this is. And so the outrage was quite significant. And within 2 weeks, Chemours came to Wilmington, North Carolina, some of the officials from the company, and they said two things. So the first was they said they would stop discharging processed wastewater into the Cape Fear River. The other, which was really striking, was they said, we've been discharging Gen X since 1980. And that was something that we really didn't fully understand at first at all, because supposedly they were making Gen X as a replacement for PFOA not until 2010. Well, it turned out that when they make vinyl ether as a byproduct, they make Gen X and all of these other fluoroethers that were found in the water. So when you go back to the consent order, right, it's also important to read the fine print. The EPA has a template, and in this consent order, it says, if you discharge a chemical that is a byproduct, if it's produced not for commercial purposes, this order doesn't apply. Right? So it's perverse, right? And so Chemours was making Gen X in a closed loop system for commercial purposes and did not discharge Gen X from that by complying with the consent order. And over here at the same facility, they were making vinyl ethers and lots of Gen X as a byproduct, and they just discharged it, right? So, and they were doing this since 1980, and then we dug further, and Chemours and DuPont were well aware of this for a long time. They were already doing toxicological studies on Gen X in in the 1960s. So they knew very well what kind of chemistries they were producing. So, of course, the skeptic that I am, I said, well, let's see whether they really will do this. So we got a lot of water samples during this time in June, just before they said they would stop discharging processed wastewater. Back then we semi-quantitatively estimated about 40,000 nanograms per liter in the water. Ended up being, we were off by a factor of roughly 2 by doing the semi-quantitative work. But, a month later, and then a few months later, the levels had dropped dramatically. So this is where this forever chemical concept is sometimes confusing to communities, right? They think if a river is contaminated with PFAS, it's always contaminated with PFAS, right? We just move the PFAS out into the Atlantic Ocean where they still are. So they're forever here, right? But they're not forever in the river, right? So communicating that is sometimes difficult. Even though this bar looks low, those PFAS levels were still high compared to most drinking water plants in the country. So other things that happened in 2017, our Department of Health and Human Services very quickly established a health goal for Gen X at 140 nanograms per liter. And now the drinking water standard for Gen X is 10 nanograms per liter, right? So the drinking water standard for PFOA as of April of last year is 4 nanograms per liter. Gen X is 10. If that's your favorable toxicological profile, it's not that much more favorable, right? So we just replaced one toxic substance with another, and we call that regrettable substitution, right? So whenever somebody tells you, oh, we're phasing out this and we're making that, right, you should ask about what is that, this new stuff, right? Is it any better? Also, working with an epidemiologist in our Center for Human Health and the Environment, we wrote very quickly an R21 grant to NIEHS, and we began the Gen X exposure study. So by November of 2017, we were actually collecting blood and urine samples in Wilmington, North Carolina. So this is work that's led by my colleague, Jane Hoppen. And what we found was that these fluoroethers, the longer chain fluoroethers, were basically in everybody in the community in Wilmington in the blood serum. And we've been tracking people over time. And you can see that the levels of these compounds in people's blood are dropping, right? So this is something that is very positive. I feel like out of all the things that I've done in my career in terms of impact on real people, I think this has been right at the top. I think this is something that really only happened because of many things kind of coming together in a fortuitous way, in a way, because it could have been just that somebody would have also ignored our paper and the newspaper article, right? And nothing would have changed, right? That could have very well been an outcome. But somehow the stars were aligned and things actually did change. So we've also been able to estimate human half-lives for these compounds in people, right? So that's also a unique opportunity to track these fluoroether levels in people. And we don't just publish these results in papers, but we also stay in touch with the community. So as part of our Center for Human Health and the Environment, we have a community engagement person, and we regularly update people in the impacted communities with results from our research. And it's amazing to see, right? And in 2017, this came out to light, and even now we're what, 8 years later, lots of people come to these community meetings, right? Like people are really very engaged and want to hear what we're learning. So let's go a little bit to the local community. So in 2018, our DEQ started collecting rainwater and wanted to look at PFAS levels in rainwater. So here's the fluorochemical plant, and these are all different rainwater samples, and the Gen X levels were up to 800 some nanograms per liter in the rainwater, right? So that's pretty crazy too, I feel, right? And it's raining PFAS basically on these people and these communities. And as a result of that, thousands of private wells are contaminated up to more than 20 miles away from the plant. So everybody with the red dot qualifies for whole house filtration, and everybody with the yellow dot qualifies for up to 3 under-sink reverse osmosis systems in their home to either treat all of the water in the house, or at least the water that is used for drinking, cooking, brushing your teeth. So I would say, this community is much more impacted than the people in Wilmington, because in Wilmington, once they stopped discharging the wastewater, right, the PFAS were pretty much gone from the water. And the biggest question for the community in Wilmington is pretty much, what have 40 years of exposure done to us? Right, that didn't go away, right? People were exposed for 40 years, and what is that, the potential health outcomes that resulted from that exposure? But this community, right, the groundwater, you can't just clean from one day to the next, right? Groundwater moves very slowly. And based on some of the work that we've done with hydrogeologists, we think that it will take many decades before the PFAS will reach levels that are safe from a drinking water quality perspective. And in addition, all the soil is contaminated, and people have grown their own fruits and vegetables, they hunt, they fish, right? Their lives are much more impacted because, their kids would swim in the lake and now they can't. They would hunt and they feel like now they can't either eat the deer or eat the fish. And so it's a very different kind of impact. I'll maybe skip over this real quick. So the North Carolina legislature also got very interested in this from a standpoint of, well, if this happened in Wilmington, North Carolina, and in the Cape Fear River Basin, are there other hotspots around the state? And so very early on, we looked through the entire public water systems in the state, and we basically found that the vast majority of drinking water sources were pretty clean. So it's generally the exception rather than the rule that you have very high contamination of PFAS in drinking water. Our DEQ reached a consent agreement with Chemours in terms of remediation requirements. Some of the things that Chemours is obliged to do as a result of this consent order is they need to sample private wells until they reach basically the edge of the contamination. They need to implement remedial strategies at the plant. They built a barrier wall between the river and this contaminated groundwater. They basically capture all of the groundwater that was seeping to the river and are treating it before it gets then discharged to the river. So that led to a substantial drop in PFAS levels beyond just stopping the wastewater discharge. And then because of the air emissions, they also installed a thermal oxidizer to basically burn the PFAS that were in their air emissions. So since this discovery, the plant spent well over $100 million on pollution abatement, but that's pennies for them, right? And if you think about it, right, and this is a Fortune 500 company that had operated, or companies, right, first DuPont, then Chemours. They were unwilling to spend pennies on their profits on pollution abatement, right? Only until they really had to. And in 2020, we got our Superfund Center funded, and we're working at understanding human exposure, immunotoxicity, bioaccumulation of PFAS in the food chain, and remediation. But an important part of this center is also the community engagement core, right? So we always look for questions from the community. We listen to them. What are your concerns? And also we share our results with the community. Probably the question I get most is home filters. So we wrote a paper on home filter performance, and under sink reverse osmosis filters are basically able to treat all PFAS to below quantification limits. So I would say every week I get probably 2 or 3 emails on home filters that I answer. And then also the question is treating the water enough? If we have clean water for the community that lives right around the plant, there were questions about contaminated fruits and vegetables. And we just published a paper on PFAS levels in fruits and vegetables. And just looking at these numbers, nanograms per gram of fruit and vegetables, it's maybe a little bit hard to understand what these levels mean. But what we saw is that these fluoroethers were in some cases present in 100% or close to 100% of the samples. And so we basically looked at, well, if the drinking water standard for Gen X is 10 nanograms per liter, and kids or adults drink this much water on a day, how much fruit and vegetable would it take to reach the drinking water limit, right? And so at 2 of the sites, very low grams of produce per day would reach the drinking water equivalent level, right? So 28 grams of blueberries looks like this. At sites A and B, right, it would have taken less than that to reach the exposure that you would have gotten from drinking water at the drinking water maximum contaminant level. And this is the daily recommended produce intake that EPA has, right? So both for kids and adults at sites A and B, you would reach that level very quickly. And these are fairly new data, and we were supposed to present this to the community a few days ago, but we had a snowstorm in North Carolina, and when it snows in North Carolina, everything shuts down. And so we have a new date to share our results. And so some take-home messages. We're all part of this, right? For better or worse, we purchase things and we don't know always what we're buying. And there are lots of unknown unknowns. We've only scraping the tip of the iceberg. There are many other things that we need to better understand. And so, working on non-target analysis, effect-directed analysis, these kinds of things are really important. Come visit us. And thank you. It's my current crew of people, and we keep working on this as best as we can.
We have time for a couple of questions.
Thank you. I'm a terrible chemist, which I've already told you. I guess, so I have a chemistry question and more of a practical question. I'll do the practical one first, which I've asked at a previous PFAS talk. We set these limits for drinking water really, really low. And then you commented on the food bit too, but we're still using them in like our wrappers and cooking materials. So what is our, what? Well, yeah, that's the one I use. I was literally looking up which PFAS is in Glide. So where do we get most of when we ingest it? Is it coming from our food, water, or our frying pan? I guess is sort of my question.
Right. So, well, the answer, like every good researcher, is it depends, right? So, well, a lot of it depends on how contaminated your drinking water is, right? If your drinking water is contaminated, often drinking water is the primary contributor, like it was the case in Wilmington, North Carolina, for example, right? And they were far away from the fluorochemical plant, and pretty much the only way they were exposed to fluoroethers was through the drinking water, right? So all the blood serum concentrations that we saw in the community in Wilmington were because of their exposure through drinking water. But in the community that lives right around the plant, right, it looks like food could be a very important additional contributor, right? And then for communities that are not very heavily impacted through drinking water, like if you go to a town where PFAS levels in drinking water are very, very low, it's mostly your home, right? It's exposure to dust. It's and also it could be a little bit food, eggs are potentially a source, but often we don't know it very well, right? Like you can buy a dozen of eggs at the grocery store and maybe they're very clean, and you might go buy some eggs from a different source and they have quite a bit of PFAS in them. It's usually PFOS. Also, fish can be potentially an important source. So it depends a little bit on your dietary habit, what happens to be in your food, and also you know, how contaminated is the drinking water.
Okay. Okay, so now I'm gonna ask the chemist.
Wait, the online question.
Oh, sorry, go ahead.
No. Oh, there is an online one. Never mind. Go ahead.
Oh, okay, so when they made or started intentionally making Gen X
Mm-hmm.
with the ether linkages in there, I'm guessing that changed the mobility of the compound?
Gen X is about as mobile as PFHXA and PFHPA, so somewhat similar. The ether linkage doesn't do a heck of a lot. Like when you look at it's surrounded by CF2 groups on either side, and the electrons, the fluorine basically shields the ether group almost entirely. So the compound behaves more or less like a perfluorocarboxylic acid without an ether linkage.
I might be wrong, but doesn't South Carolina or North Carolina still allow the agricultural spreading of biosolids from? So where does this fit in? Where does that as a source of PFAS in our food, et cetera, fit into this whole scheme?
I would say practically all states allow land application of biosolids. The state of Maine is the one that is not allowing it right now. And again, it depends a lot. Like biosolids to me is not equal biosolids, right? You might have a lot of biosolids with quite low levels of PFAS, but then you have a community where maybe there's an industry that uses a lot of PFAS, and then you have sky-high levels of PFAS in the biosolids. And also solids from like paper mills and things like that can be extremely loaded with PFAS. So, you know, before we land apply, I think it's important to first know what we're land applying, and then focus especially on the places where we can drastically lower PFAS levels by controlling PFAS discharges at the source, like an industrial source. Yeah. Like we have one, maybe just, and so aside from the fluorochemical plant, you know, we have a community with a large textile plant, and they are coating textiles with side chain fluorinated polymers. And so these are basically particulate materials where PFAS can actually break off over time. And so we have fields where these side chain fluorinated polymers have been land applied for a long time, and we're now measuring like thousands of nanograms per liter of PFOA and PFAS running off the fields. Yeah.
Okay, let's thank Detlef.